that's the homework you turn in.
Okay.
Okay, so on Monday you turn in this homework. There's a handout on 1.1, handout on 1.8, handout on 2.1, but just up through 2.1.
Okay.
Okay, the rest of chapter 2, no, we will be doing that for quite some time. Yes? I will be sending out a practice test sometime soon. Let's say by Friday. Okay. Okay. Alrighty, so let's continue in chapter 2. Okay. So in chapter 2, or section 2.2, okay, we're going to talk more about graphs of functions. Graphs of functions. I mean, earlier we talked about graphs of equations, but now we're going to concentrate on graphs of functions, okay? I'm going to start by graphing some real simple functions whose graphs we should have memorized. We will have memorized because we're going to use these as template functions, kind of basic functions, to help us graph what are called transformations of them, modifications of them by moving them around. Okay, so first let's graph the following. Okay, so let's move that over there. Thank you. Graph the following basic functions. After we get the graphs, let's memorize the graphs. Okay, so some of these I'm sure you do know the graphs of, but we want to get really, really comfortable with them. So f of x equals x squared, x cubed, x to the fourth, which you probably don't know what that looks like. F of x equal to the absolute value of x, hopefully you know what that looks like. F of x equal to the square root of x, you may or may not know what that looks like. And f of x equal to 1 over x. Okay, so for all of these functions, we're going to graph them, and from the graphs, let's also find the domain and the range. Okay, now, on Monday we talked a lot about domains of functions, okay? We found domains of functions by looking at the formula for the function, f of x equals whatever, okay, and found the domain. We haven't talked about finding ranges of functions, okay? And we don't find ranges of functions from the formula. It's way too hard to do that. We find ranges of functions from their graphs, okay? Now, let me just draw some arbitrary function, and from this graph, let's, see how we can find the domain and the range, okay? So let's consider the graph of some function. I'm not even going to give us a formula for it. From the graph, find the domain and the range. Okay, so whatever. Y equals f of x. Now, I don't know, I'm just going to put some numbers on here. Let's say that's the point, 4 comma 6. This is the point, negative 2 comma negative 3. This is the point, negative 4 comma negative 1. Okay. All right. Now, when I want to find, well, okay, what is, when I have a function f from a set x to a set y, and I want to find the domain of the function, which set is that? The domain of a function is the set of x values, right? You know, sometimes we just say capital X, but the domain is the set of x values, you know, which have y values corresponding to them, okay? And the range of a function is what? The set of y values, you know, the set of outputs, the set of y values. Now, if you have a graph of a function in front of you, you can find its domain by, I like to take a ruler or something, some sort of a straight edge, and kind of read along the x-axis from smaller to larger, okay? Now, when you have a graph and you put a dot on it, as opposed to just, you know, making the graph go up without, or up or down without putting a dot on it, that means that the graph starts, stops there. This graph stops, starts there, whatever, stops, I guess, in that case. Okay? So, for example, okay, if I choose x equals negative 5, is there any y value corresponding to x equals negative 5 on this graph? No. Okay, there's no point on the graph corresponding to x equals negative 5. So negative 5 is not in the domain of the function. What about x equals negative 4? Is it in the domain of the function? Yeah, when x equals negative 4, y is whatever, negative 1. There's a point on the graph corresponding to x equals negative 4. Is negative 3.5 in the domain? Yes. Is negative 2 in the domain? Yes. Is 0 in the domain? Yes, there's a y value corresponding to x equals 0. Is x equals 1 in the domain?
Yes.
Yeah. Is x equals 3 in the domain? Is x equals 4 in the domain?
Yeah.
Is x equals 5 in the domain?
No.
Is x equals 4.2 in the domain?
No.
No. Okay? So the graph starts here and stops there, okay? Which means that its domain, I'm going to go ahead and color this on the x-axis. Its domain starts at negative 4 and includes negative 4, because x equals negative 4 has a y value corresponding to it, and goes all the way to x equals 4, and x equals 4, you know, is in the domain, because when x equals 4, y equals 6. Okay? So this blue interval is the domain of the function. And, okay, you know, let's go ahead and just write the domain using interval notation. We may as well. So what's that domain?
Bracket.
Okay, so bracket, negative 4, comma 4, bracket. Okay. All right, now to find the range of a function from the graph, and we definitely did not find ranges of functions from the formulas, definitely not too hard. To find the range of a function from the graph, you read along the y-axis, because your goal is to find the set of y values, so like from smaller to larger. Is y equals -4 in the range?
No.
No. Is -3.5 in the range?
No.
No. Is y equals -3 in the range?
Yes.
Yes. When x equals -2, y equals -3. Is y equals -2 in the range? Yeah, there's two different x's that give me y equals -2. Is 0 in the range? Yeah. Is y equals 3 in the range? Yeah, there's an x that gives me y equals 3. How far does the range go?
6.
Okay, up to 6. Any number past 6, 6.1, okay, is not in the range. 7 is not in the range. Okay, this is the highest point on the graph. That's the biggest y value, okay? So my range starts at -3, that's the smallest y value on the graph, and goes to 6. Okay, so this is the range of my function. Okay, so, let's go ahead and write the range in interval notation. What is it?
Bracket -3, 6.
So bracket, -3, 6 bracket. Now, it is a set of y values, that's understood, okay, but, we typically just write it in interval notation. I mean, you could write it, the set of all y, such that y is between -3 and 6, but interval notation is fine. Okay, so if we have the graph of the function in front of us, we can find its domain and its range. Okay. Now, domains you can also find just algebraically by looking at the formula. And if the function has x's in the denominator, then we got to throw out x's that make the denominator 0. If the function has a square root in it or any sort of an even root, then you can only have x values that make you take the square root or even root of a positive number or 0. But otherwise, like a lot of these functions have domain all real numbers. But the range, we need to have the graph to see. Okay, so again, I'm graphing these functions. I already wrote the instructions up there, so. Okay, let's graph f of x equals x squared. Okay, now, is there any symmetry? Any symmetry?
Yes.
With respect to the
Y-axis.
y-axis, WRT, y-axis. If you plug in, this is y equals x squared. If you substitute in the opposite of x for x, you get the same thing. The opposite of x squared is x squared. Now, even though there is symmetry with respect to the y-axis, I'm just going to go ahead and make an entire table because I want us to have these points memorized. The points from -3 to +3. So, -3 squared is 9. +3 squared is 9. That's illustrating the symmetry with respect to the y-axis. -2 squared is 4. 2 squared is 4. -1 squared is 1. 1 squared is 1. That shows you the symmetry with respect to the y-axis. 0 squared is 0. Okay, now all right. And of course, hopefully you know what the shape is. What is the shape? Parabola. Okay, so square, 1 unit, 5, 10. Okay, now, when I graph y equals x squared, which I will be doing a million times, or similarities to it, you know, I typically plot my origin, 0, 0 is my vertex, and then I have 1, 1, and negative 1, 1, again, mirror images across the y-axis. I have 2, 4, and then negative 2, 4. And then I have 3, 9, and negative 3, 9. Okay, so I want you to be that familiar with the graph that you can just plot those points without even having to, you know, make your table of values. Okay, so this is our simplest possible parabola, simplest possible quadratic function. Okay, now looking at the graph, let's get the domain and the range. Okay, well, first of all, from the function itself, without even the graph, what's the domain? All real numbers. Okay, so are there any x's you could plug in that would make you divide by 0? No, because there's no denominators. Are there any x's you could plug in that would make you get the square root of a negative number? No, because there's no square roots. Okay, those are the only two things we have to worry about right now. Okay, later there'll be other things, but for now that's it. Okay, no denominators, no square roots. The domain is the set of all real numbers. Or if you like, you know, interval notation, negative infinity to infinity. Now, let's just look at the graph and make sure we agree with that. Okay. So, you know, as we read along the x-axis, okay, even though you can't see some of these points, like we can see negative 3, 9, we can't see negative 4, whatever, it would be 16. We can't see negative 5, 25, okay? But this parabola, not only does it go up forever, it goes out to the left forever and out to the right forever, albeit very slowly, you know, because at negative 4, the y value is 16. At x equals negative 5, the y value is 25. But, you know, this graph is going out to the left and it's going out to the right. So no matter how far out I go to the left, there is a y value corresponding to that x value. And no matter how far out I go to the right, there is a y value corresponding to that x value. Because again, the graph goes out to the left and out to the right forever. Now, the range of the function, we really can't find the range just from the equation. We really need to have the graph in front of us, or at least, you know, thinking about what the graph looks like. Okay, so for the range, okay, is y equals negative 2, whoops, let's see this. Is y equals negative 2 in the range?
No.
No. Is y equals negative 1 in the range? No. Is y equals 0 in the range? Yes. Okay, is y equals 1/2 in the range? Yeah. Is y equals 1 in the range? Is y equals 5 in the range? Is y equals 10 in the range? Is y equals 1,000 in the range?
Yes.
Yes, okay. So my range starts where? What's the smallest y value in the range?
0.
0. And then it goes on forever to infinity. How could I write that in let's just write the old-fashioned notation. Old-fashioned notation would be, I mean, it's not really old-fashioned, but set builder notation. The set of all y such that y is greater than or equal to 0. Okay, so that's set builder and inequality notation. Or in interval notation, what would we have?
Bracket 0, 0.
So bracket 0, comma infinity. Okay. Okay, now let's look at f of x equals x cubed. Does y equals x cubed have any symmetry?
Yeah.
Yeah, it does. What kind of symmetry is it going to have?
Is that origin?
With respect to
Origin?
the origin, yeah, the origin. So symmetric with respect to the origin. How do you test an equation for symmetry with respect to the origin? All right, you substitute in the opposite of x for x and substitute in the opposite of y for y. Okay, so if I have opposite of y, I'm just going to test this symmetry because I think you need review of it. So negative y, substituting for y, opposite of x, quantity cubed instead of the x cubed. Now, opposite of x cubed, like negative x times negative x times negative x. We have 3 negative signs is negative. And then we have just x cubed. Now, the question when you're testing for symmetry is, do you get the same equation after you do your substitutions? Is that the same equation as the original one? Well, can I do something with it that might make it the same? I got negative signs on both sides. So, okay, if I just multiplied both sides by -1, which is legal and certainly does not change the solutions to the equation, then we would get y equals x cubed, the same equation. Okay, now what I'd like you to remember is whenever you have y equals or f of x equals something with only odd powers, this test for symmetry is going to apply. And the graph will be symmetric, is symmetric with respect to the origin, when you have only odd powers of x on the other side. Okay? And later we're actually going to call these kinds of functions odd functions. So I wanted to review that for there. Okay, so now let's just make a table of values. And we'll also see the symmetry happening in the table. Not the same kind of symmetry as you had before, but now I probably won't actually plot this point because the y value is so big, or I guess small, but let's just see where it is. -27. When x is -2, y is -2 cubed or -8, I will definitely plot that one. When x is -1, y is -1 cubed or -1. When x is 0, y is 0 cubed or 0. Now, when your graph is symmetric with respect to the origin, like this one is, when you plug in the opposite of what you plugged in before, like when I plug in +1, I should get the opposite of what I got when I plugged in -1. I don't get the same value, but I should get the opposite value. So I do 1 cubed or 1. So the x's are opposite and the y's are opposite. That's what we mean by symmetry with respect to the origin. Okay, similarly, when I plug in 2 cubed is 8. So -2 comma -8, +2 comma +8. The x's are opposites and the y's are opposites. And same thing for 3, 27. Okay. Now, okay, I want us to get familiar with this graph as well. I want to at least go up to the 8 and down to the -8. I won't bother going up to 27 or down to -27. Okay, so again, I'm not gonna plot, you know, that one or that one, but I will plot -2 comma -8. Let me just plot +2 comma +8, the same, you know, right after that one. +2 comma +8. Those 2 points are mirror images, sorry. These 2 points, when their x's and their y's are opposites, those 2 points are mirror images, reflections of one another through the origin. Okay? Then I have -1 comma -1, and then +1 comma +1. Again, those 2 points are mirror images across the origin. And then I have 0, 0, the origin itself. Okay? Now, if you had never seen this graph before, you know, never seen anybody graph a cubic function like this, then you'd have to have a lot more points. Okay? These, you know, 5 or even 7 points would not be sufficient. Okay? Okay, what one might do, okay, like in my Math 60 class, is one might have a computer plot a whole bunch of points, okay, because computers can do things faster than we can. So I might plot a whole bunch of points, like 100 points between -2 and +2, say. And if we did that, we would get this shape. So it's going down there, you know, remember it's got -3 comma way down there, -27. And then it goes up to that point, and then to there. On this side, when x is negative, the graph is like an upside down parabola. It's not a parabola, but we say that it's concave downward. And then at 0, 0, it changes to concave upward. So to the left of 0, it's like that, and to the right of 0, it's like that. And a point on a graph where the graph changes concavity is called an inflection point. And when you get to calculus, you study a lot about inflection points. So when you draw y equals x cubed, f of x equals x cubed, I want you to, you know, kind of really emphasize, you know, that it's concave down this way and concave up after 0. Okay, so I want us to, you know the shape of that graph and also these 5 points. -2 comma -8, -1, -1, 0, 0, 1, 1, and 2, 8. Okay? So that you could just very quickly graph that cubic function. Okay, now let's see. Let's get the domain and the range of the function from the graph. Where is that? Well, whoops. First of all, the domain we can get just from the equation. So what's the domain of f of x equals x cubed? All real numbers. Okay, are there any x's in denominators? No, because there's no denominators. Are there any x's under square roots? No, because there's no square roots. Those are the only two things that can go wrong right now. Okay, so I can plug in any x whatsoever and cube it. Nothing's going to go wrong if I take an x and I cube it. So my domain is, again, the set of all real numbers. Now, looking at the graph, okay, and reading along the x-axis, okay. Now, again, this graph goes down forever and up forever, but it goes out to the left forever, again, rather slowly, and out to the right forever, again, rather slowly. You know, for example, at, x equals -2, y is -8. At x equals -3, y is way down there at -27. At x equals -4, y is way down there at -64. Okay, but this graph does go out to the left forever and also out to the right forever. Okay, so every single real number is in the domain of the function. What about the range of f of x equals x cubed? And if you want to say -infinity to infinity. So what about the range from the graph? All real numbers, okay? So this graph is, going down forever, going up forever. Every single real number is in the range, okay? So range is set of all real numbers, or if you like, -infinity to infinity, okay? Okay, now let's look at, f of x equals x to the 4th. Okay, now, probably haven't ever seen this one. This one's graph. Any symmetry? Symmetry with respect to what? Y-axis. If you plug in -x for x, -x to the 4th is the same as x to the 4th. So this graph has symmetry with respect to the y-axis, as does any function that equals only even powers. Only